All right, hello everyone, and welcome to Astronomy on Tap Triangle. Tonight we are going to learn about the invisible lives of galaxy groups and black hole hunting. It's going to be a great set of talks. We are going to get those started in just a few minutes, but in the meantime, here are some fun trivia questions to get us started. So the first question is, what is the most common type of galaxy? Go ahead and throw the answer that you think in the chat, and I'll give you a few minutes to think about it and then give you the answer. All right, I see a few guesses in the chat, but the most common type of galaxy is actually the elliptical galaxies. You might have gotten a hint from that, as that is the type I have pictured on the right here. For our next question, which galaxy holds the first imaged black hole? So this was hot on the news a little while ago. This is the first image ever taken of an actual black hole. And the question is, what galaxy is that in? All right, so the answer for this one is M87. So the first one, Milky Way, that is where we live. Unfortunately, we cannot see the black hole at the center of our galaxy because we're in our galaxy and there's just too much stuff. M31 is the Andromeda Galaxy, our closest neighbor. That's not the one they looked at either. And then M104 is the Sombrero Galaxy, which is just kind of a fun one to look at. And then for our last trivia question, and the trickiest one, what is the most distant known galaxy? So your options here are all wonderful strings of letters and numbers. J0313, 1806, GNZ11, SN1000 plus 0216, and 2018 AG37. I'll give you a few minutes to think about that one. All right, and the answer here is GNZ11. All these other ones are the most distant something, but none of them are the most distant galaxy. This top one is the most distant quasar ever observed, the most distant supernova, or the most distant solar system planetoid. And I see our co-host Josh has been putting in the chat some of the ways to interpret these odd strings of letters and numbers. So I'll explain that a little bit. So J tells you that this is a 2 mass. It's from a survey that always starts its catalogs with J. And then these are a shortened version of the coordinates at 3 hours and 13 minutes. Oops. And negative 18 degrees and 6 minutes. Same for this one. It's 10 hours, 0 minutes, 2 degrees, 16 minutes. This is a solar system object, so it is named after the year it was discovered. And then I'm not actually sure what these numbers are. I think possibly initials of the author of the paper. And this one, maybe one of our Galaxies presenters today can tell you, but I'm going to confidently make up that it stands for galaxy number and then it's redshift, which is 11, Z11. But yeah, those are our trivia questions for tonight. I'll now get us started with our intro talk. So tonight our theme is galaxies and black holes in galaxies. So I'll give us a little bit of an intro on both of those subjects. So the first question is, what is a galaxy? This is sort of a really interesting question because astronomers didn't actually start to figure out what a galaxy was until the 1920s. Prior to that, we had seen lots of galaxies, but no one knew what they were. They were considered spiral nebulae, just another type of nebula, like, say, the Crab Nebula or the Orion Nebula, just another type of nebula. And that was the dominant idea about what galaxies were until the 1920s. In the 1920s, that was the subject of a huge debate, what these galaxies were. And it was actually settled when they finally measured the distance to a galaxy, to a spiral nebulae, and discovered that it was further away than anything else we had ever measured the distance to. It was way outside any of the stars that we had measured, any of the nebulae we had measured, anything else. And because it was so far away, we could also figure out that it was huge, absolutely ginormous compared to anything within our own galaxy. And that is, of course, because it is a galaxy all its own, just as big or even bigger than our own galaxy, and just really far away in the universe. And that sort of began the modern study of galaxies, which has come a very long way in the approximately 100 years since we really started working on it. So the sort of first question about how to tell what a galaxy is what is it made of? So you can say maybe that a galaxy is a bunch of stars all put together, but a lot of things are a bunch of stars just put together. Star clusters are a lot of things just put together. Globular clusters are a lot of stars put together. So are dwarf galaxies and galaxies. So it can't just be that. There has to be something else to it. So the first thing that galaxies are made of is stars. In this image here, you can see some of the stars in the galaxy, these little tiny specks of light. Most of the time we can't see individual stars in galaxies because they're just so far away. But sometimes you can see them, especially things like supernova. The next thing that a galaxy is made of is gas. So this sort of starts to distinguish it from some other clusters of stars. And you can see in this image some of the sort of white light around here. That's maybe some of the gas in the galaxy. Next up is dust, which is, you can see here, it's these dark parts. That's where the dust in the galaxy is, and they're darker because the dust is blocking the light coming out of those areas. The next thing that galaxies are made of, which is really one of the important defining features of a galaxy, is galaxies have dark matter. They have lots and lots of dark matter in them and surrounding them. So we actually first learned about the existence of dark matter by studying galaxies and seeing that galaxies acted as though they had more mass than they should by looking at them. And that was our astronomers' first discovery of dark matter. And now we know that galaxies all have a lot of this dark matter. They have it in where they have their stuff, but they also have it in a huge area surrounding all the light up stuff. They're dark matter halos, which are much, much larger than the visible parts of the galaxy. And that's really an important defining feature of a galaxy, is that it has that sort of dark matter halo. And then the last thing I've put is black holes with a question mark. So we'll talk a little bit more about this later, and then maybe Mugdha will tell you a lot more about this in our second talk of the night. But many galaxies appear to have supermassive black holes at the center of them. And we don't know if it's all galaxies, and we don't know exactly what the interactions there are. That's one of the big defining questions about galaxies right now, is those supermassive black holes at the center, and if they're always there and how they get there and things like that. But that may also be a defining feature of a galaxy. The next sort of set of defining features of a galaxy is how big it is. So this is again where the galaxies sort of distinguish themselves from other groups of gas like nebulas or stars like clusters. So galaxies are much, much, much bigger than any of those things. Galaxies have billions of stars in them. So for example, a very large stellar cluster within our own galaxy might have thousands of stars in it. That's a very large one. A dwarf galaxy might have millions of stars in it, but a galaxy will have billions of stars. Galaxies are thousands of light years across. Our own galaxy is about 50,000 from one edge to the other. And they also contain, this is hundreds of billions of solar masses in mass. So they're much, much bigger than something that contains, a couple million or even thousand or even million solar masses worth of mass, like a dwarf galaxy. And the lines between there are a little bit fuzzy, but in general, you want billions of stars and thousands of light years across. And that is what makes a galaxy. Our second talk, like I said, is about black holes. So the first question that you might come up is, what is a black hole? So black holes were first theorized about in the early 20th century, around there, as sort of the result of what happens when you have a very massive star that has a ton of mass, and then it runs out of fuel, so it can no longer support all that mass. It would collapse, and it might collapse into something like a black hole, which is, at a very basic level, just an extremely large amount of mass in an extremely small area. It's a very, very dense, small object. The thing that makes black holes really interesting, though, the first thing at least that makes black holes really interesting, is that they are so dense that even light cannot escape their gravitational pull. So we can't see them. So we have to observe them using other means. Because we can't see them, we observe them by looking at their ripples that they create around them. Just like if I had an invisible rock and I threw that rock into a pond, you would see the ripples from the rock being thrown into the pond. You could even, if you wanted to, through a lot of experiments, you could try and figure out how large the rock I threw into the pond was based on how big the ripples were that came out of it. So you could learn about the rock by studying its effect on its surroundings instead of the rock, even though you can't, because you can't see it. So we do sort of a similar thing with black holes, which create these ripples, not in water because they are in space, but in space-time. And to give sort of a very brief explanation of how that is possible, we have to look a little bit at the theory of gravity. So if you are a regular at Astronomy Untitled Triangle, you might remember some of this from our talk on gravity a few months ago. But basically what it is that gravity, Newton's basic theory of gravity says that mass pulls another mass. Then Einstein took this theory and he changed the theory, and he changed how we even fundamentally think about gravity. And he said that mass creates distortion in space-time. So sort of the difference between those theories might be exemplified by looking at this image here of the sun, and you can see it's sort of a cartoon of the sun as if it is pulling on 2D space around it. So if we think about this like Newton would think about this, we have the sun, and it is a massive object, and thus it exerts force on the Earth, which is another massive object near the sun. And because the sun is exerting force on the Earth is going to orbit the sun. It doesn't exert enough, it doesn't have enough to pull away from that force. If we look at this sort of more in an Einsteinian way, we would say that the sun is creating this distortion, and the Earth is inside the distortion that the sun creates. Unless it is moving fast enough to get out of that, it's going to be stuck there and sort of move around the sun in the distortion. You could sort of think of the little coin tornadoes that they sometimes have in the stores. If you just sort of plop a coin down without really giving it any speed, it's just going to fall right to the center. If you give it a little more speed, it'll go a little bit around. A little more speed will go around a lot. If you really chuck that thing at the coin tornado, it's going to go rocketing out the other side. So the same sort of distortion idea applies here. You have to have enough sort of speed and enough mass to get out of the little pull of the pull of your massive object. And the more massive the object, the larger the distortion. So you can see sort of, here's the sun, and then something more massive creates a larger pull, and something more massive creates a larger pull. And then we have a black hole, which is so massive that it creates a pull that even light doesn't travel fast enough to get out of. And that is sort of the basic idea behind black holes. So if we go back to this image, we can see that there are some oddities in it. Those ripples created by the black holes. So we can see there are stars in this image. Here's one, and there are galaxies, but there are also these weird streaks. And these streaks are actually light that has been pulled out of sort of its normal path that would get to us and show us the star or galaxy or whatever it came from. And they've been distorted because they traveled near that distorted space-time near a very massive object. In this case, that massive object wasn't a black hole, but if you traveled sort of close to a black hole, but not close enough to fall in, the light would get bent in just the same way. So that is the sort of ripples that we can see that black holes create just by existing, just by sitting there and pulling light and stuff near them. Black holes are not content to just sort of sit there. They also do lots of interesting stuff when they interact with the mass around them. So this shows one example. This is a set of 4 images from 2 different telescopes at 2 different times. So the top images are in UV and the bottom images are in visible light. These ones on the left are from 2009 and on the right from 2010. And these are all of the same very distant galaxy. And you can see the arrow points to sort of the center of the galaxy. In 2009, you can't even see it in the UV. It's not even visible here. And then a year later, it is brighter than everything near it in the UV. Something happened that made this very bright. And we can see the same thing happens in the visible, maybe not quite as dramatically. You can see it here in the visible light, and then a year later is a lot brighter. So something changed at the center of this galaxy that made it suddenly emit a whole lot of very high energy light. And the centers of galaxies tend to do this sort of thing fairly often. And those are known in astronomy as active galactic nuclei, which are weird things at the centers of galaxies. And for a long time, astronomers knew about them, but didn't know what they were until we connected the theory on black holes with the observations of active galactic nuclei. So what is actually happening here is there's a black hole at the center of this galaxy, and a large star has been orbiting it, and then at some point it crossed a threshold, and the black hole took a whole bunch of it, and it emitted a whole bunch of light, a whole bunch of very high energy light, which we can see in these images. So we can see that galaxies, they don't just bend light, they do a whole lot of very interesting things. And Mugdha is going to tell us a lot about that in her talk. But first off, we have the first talk of the night, which is going to come from Zack Hutchens. So Zack may be familiar to some of you if you hang out at Astronomy on Tap every month. He is one of our coordinators. And we're really excited for him to present his own research tonight. Zack is a third-year PhD student at UNC Chapel Hill, where he studies gas in galaxy groups with Dr. Sheila Canopin. He is a member of both Resolve and LADUMA, which are 2 large surveys of galaxies at different points in cosmic history. And then he earned his BS in physics from High Point University in 2018. So I'll hand it over to Zack.
Thank you, McKenna. Thanks for the awesome intro talk. I'm going to go ahead and share my screen. Okay, I hope everyone can see the screen now. Can hear me okay? Is that correct? Okay, so as McKenna said, my name is Zack Hutchens. Today, I'm going to be talking about the invisible lives of galaxies. I'm a third-year PhD student at UNC Chapel Hill. And as McKenna mentioned, Mugdha and I, we study using galaxy surveys. So we're not looking at one galaxy at a time, but we're looking at thousands of galaxies at a time and trying to understand patterns and trends in their behavior, colors.
Sorry, Zack, we're not seeing your screen.
Oh, you're not? I'm sorry. Let's try that again. Okay, sorry about that. Can you see it now?
We can see it now.
Okay, sorry about that. So I'll go ahead and get started. So I'm going to repeat a little bit of what McKenna said, but what I want to do first is give you Galaxies 101. So as McKenna mentioned, galaxies are these collections of gas, stars, dust, and dark matter. And unlike some other astronomical objects you might think about, like stars or planets, galaxies have very complex external structures. They might have spiral arms, disks, bars, bulges. So each one is a little bit different. The typical radius of a galaxy is about 50,000 light years, which means that if you're on one side of the galaxy and you shine a flashlight to the other side, it takes 50,000 light years for that beam to cross it. So they're very immense compared to our everyday scale of understanding. And we actually live in a galaxy. Our own sun orbits in the Milky Way galaxy. And this is an artist's illustration on the right of what the Milky Way galaxy might look like. But to us, since the Milky Way galaxy is a disk and it has spiral arms, since we're inside it, it actually looks like a disk. So just more like a straight line, which is what you're seeing on the left. And if you've ever had the pleasure to go somewhere really dark and see the Milky Way with your own eyes, that's what you would see. And I hope you get that chance. So if you go out into the universe with a telescope and you make a map of all the galaxies, one thing you'll notice is that the galaxies are not distributed evenly. If they were distributed evenly, so this is a map of galaxies in one of the catalogs that we run here at UNC Chapel Hill. If these galaxies were distributed evenly, you would say that they're all roughly the same distance apart from each other, but you can tell that they're not. In fact, there's these really dense concentrations of galaxies, which are called clusters, and there's some less dense concentrations called groups, and all of these are connected through these filaments. Between the filaments, there are these voids, and this complex structure is a really important way of telling the story of what galaxies are. The reason for this structure is gravity. So gravity pulls things together. It takes smaller structures and merges them into bigger ones. And this is a simulation that you can see in this GIF of the evolution of the universe. And you can see that all the galaxy groups and clusters are forming from smaller units, and then they're building up hierarchically through cosmic time. So you start without smaller things. So you start with smaller things, and they build up gradually into the large concentrations of mass that we see here today in these filament and void structures. Now, many galaxies do live in these groups. Some are isolated, but many live in groups or clusters, and we are no exception to that. So our own Milky Way galaxy lives in a group called the local group, and the local group basically has two main galaxies, the Milky Way and Andromeda, which is M31, and they form sort of this dumbbell shape. And so it's this dumbbell shape, and then around each of the major galaxies and triangulum, you sort of have these more dwarf galaxies. The local group has a mass of about 2 trillion suns, which is really heavy because the sun is already really heavy. And we have a diameter of about 10 million light years. So it's a very large structure in terms of the time that a beam of light would need to traverse it. So if we go back into the galaxy catalog, we can use computer algorithms, which is most of what my work has been on, to try to identify groups of galaxies based on just their positions and their velocities and things like that. And so I won't get into the details of this histogram, but what this is showing is that the largest groups are the most rare. So this is showing the number of groups on the y-axis, and then how many galaxies are in that group on the x-axis. So you can see that we only have one group, which is basically a cluster of about 235 galaxies, whereas we have almost 10,000 groups of size, maybe 2 to 5 galaxies, which are more like our local group. So these very massive structures with lots of galaxies are actually the least common. So here's another example of a galaxy system besides our own local group. This is the Coma cluster. This is actually the NASA astronomy picture of the day 2 years ago in March 2018. And the Coma cluster is extremely massive. It has over 1,000 galaxies in this cluster, and it has a mass of over 700 trillion suns, and its diameter is about 20 million light years. So you can see in this picture, there's these two very prominent giant elliptical galaxies, and then almost every other object, with exception for some stars, are galaxies and are members of this cluster when you look at this image. And this is an image that is taken in the optical, which is sort of an astronomy jargon word for visible light. So it's light that our eyes could see. So one thing you might ask when you see a picture like this is, what are we missing by just looking at this with our eyes? So that's what my talk is going to be about, the invisible lives of galaxies, what we can't see with our eyes. So if you ask, what is this picture missing? There's basically two answers that I'm going to talk about tonight. One, other types of radiation that our eyes can't see, and then two, dark matter, as McKenna mentioned. So let's go ahead and get into the first thing, other types of radiation. Now, if you think back to maybe your high school physics or chemistry class, you will have learned that light is a wave. And just like all waves, they have different wavelengths, different frequencies, and that corresponds to its energy. So light is an electromagnetic spectrum, is what it's called. And you can have everything from extremely energetic X-rays, gamma rays, down to radio waves, and everything in between. What we can see with our eyes, it's called visible light, is just this one tiny box on this entire spectrum. So if we were to only look at galaxies with our eyes and galaxy groups with our eyes, we'd be missing a huge part of the story. So what scientists have done instead is invent instruments that can detect radiation from other wavelengths of light. So I've sort of listed a few down here. So this is the Chandra. This is the Chandra telescope. It's an X-ray spectrometer. So it's measuring extremely energetic radiation from space, things that are very hot and energetic. This is the SOAR telescope, which is actually the main telescope that McKenna, Mugdha, and I use at UNC. And this is a telescope that detects what we can see with our eyes, just at a much more sensitive level. And this last telescope is the Green Bank telescope in West Virginia, and it measures radio waves, just like your car would measure radio waves when you're listening to the radio. So because of all these tools, we can look at the story of galaxy formation and the story of galaxy groups in literally a whole new light. So one way to do this is to look at the X-ray. So this is the Coma cluster again. On the left, you're seeing the optical image. That's the picture I showed you before. And then on the right, you're seeing the X-ray image from Chandra. And you can immediately see that once you include the X-ray light, we're seeing much more of the group than we had before. There's all of this purple stuff is what Chandra detects to be X-ray gas at more than 1,000,000 degrees Kelvin. And so you can see there are these complex streams that are not only located within the galaxy and within the group, but they're between the galaxies in what's called the intergalactic medium. And so by having this X-ray, we're actually seeing a lot more of the group than what we could see with just our eyes. Now, one effect of such an X-ray gas, and there are many, but one is called ram pressure stripping. So if you have a galaxy that's moving through this group that has this hot gas in here, that galaxy, as it moves, fills this hot gas as kind of like a wind, almost like if you're riding a bicycle, you feel the wind on your face, on your arms. It's like that. It fills this as a wind, and that actually strips the galaxy of the gas it has inside of it. And you can end up with these complex, they're called jellyfish galaxies, where they have these sort of tentacles coming off, where you have a lot of gas and stars inside of them because it's being stripped by that hot gas as the galaxy moves through the intergroup medium. And so that's something that without X-ray technology, we actually would not be able to explain that very easily. So having this X-ray technology, looking at galaxy groups in the invisible, is a really cool way of advancing our knowledge of galaxy evolution. Now, here's another way of thinking about that. So our eyes also cannot see radio waves. So this is a picture of the M81 group. So this is a fairly small group, especially compared to the Coma cluster that you just saw. But again, on the left, you have the optical image. So this is what you would see with your eyes, although it's black and white because that's how the computer processed it. And then on the right, you have the radio image at 1420 megahertz. And that may sound unfamiliar, but you're probably used to using megahertz every day if you're commute to work and that sort of thing. If you listen to 100.1 on the radio station FM, that's 100.1 megahertz. So in principle, if you could tune your radio up to 1420, if you had that channel on FM, then you might be able to detect some radio from galaxies if it were strong enough. But for astronomy, 1420 megahertz is actually a really interesting frequency, a channel to look at in the radio, because that's where hydrogen emits, the most common element in the universe. So if you look at this image of galaxy groups on the left, these three galaxies, you might say, yeah, these galaxies are close together, but that's really all they are. They're not really interacting or anything like that. They're sort of distinct, and that's all you would think. But when you look in the radio, like on the right picture, you get a totally different story. So radio is showing the cold hydrogen gas, And there are these really complex streams that flow within the galaxies and around the galaxy. See, there's a lot of rotation. You can also see, if you look at, for example, this galaxy and then this galaxy's image in the radio, you can see that the gas is extended much more than what you'd get from just the stars in the visible light. So you're really telling a lot of different story here, which is pretty cool. And one of the important reasons that we might want to study gas is that gas is actually radio detected hydrogen gas is the raw material for star formation. So gas condenses down from these streams from the intergroup medium, the intergalactic medium, and it condenses onto the galaxies, and there it's nurtured into an environment where it can actually fuel stars, fuel the formation of stars. It can fuel active galactic nuclei that Mugdha is going to talk about. And it's really the raw material that a galaxy needs to grow. So if you did not have this radio image, you're missing a huge part of what this galaxy's life story is, if you were only just look at the optical. So that sort of covers a brief view on the other types of radiation that we can see in galaxy groups. Of course, there's a lot of other examples. You can look at infrared, microwaves, and so forth. But I kind of want to jump into to the second thing. So by looking at an optical image, and any image for that matter, radio, X-ray, whatever, we're missing dark matter. And McKenna sort of touched on this in the beginning. But dark matter was actually discovered by a man named Fritz Zwicky. You can see his very flattering picture on the right that was taken in 1933. And he figured out that, or he proposed that dark matter might exist because he studied the motion of galaxies and clusters. So if you remember back to basic, like introductory physics of high school, college, if you took that, you'll remember that if you know the velocity of an orbit and the radius of the satellite that's orbiting, that tells you about the mass that's enclosed by the satellite that's orbiting. So what Fritz Zwicky did was he looked at galaxy clusters, and he looked through a telescope where you can measure how fast are these moving. You can measure how fast they are, how fast they are moving from the group center and where they are located. You plug that into your physics equation and you predict a mass, right? So you say the galaxy cluster should have this much mass. And what you do if you do that calculation for galaxy cluster and looking at the galaxies that are moving within the cluster is that it doesn't check out. You need a lot more mass to produce that. And that was the original motivation for saying that there has to be some kind of additional mass that we're not detecting. And that's why it's called dark matter. So dark matter really means, dark means you can't see it, and matter means matter. So it's kind of a funny word, but that's what it is. So we think now that dark matter actually accounts for about 85% of the universe's total mass. And it's likely not what we would call normal matter. So in astronomy jargon, that's called baryonic mass. That's what you're used to seeing. You're made of baryonic mass. The Earth is made of baryonic mass. All the elements are baryonic mass. So the reason we think it's not normal mass is because we've basically explained away every mechanism that it could be some type of non-mysterious matter, except for very invisible gas that would be hard to detect. It's hard to separate that from what dark matter is. So a lot of research is going into, is this just a new type of particle in general? We have the standard model of particle physics where everything is made out of these fundamental particles. And the dark matter problem is making physicists think that maybe there's more than maybe there's more than what we know about. And it might be in the next few years that some of these, we might discover a new particle that explains the missing mass in the universe in terms of dark matter. I wanted to point out, this is a dark matter structure simulation. So even though you can't see dark matter with a telescope because it doesn't interact with light, doesn't absorb light, doesn't emit light, we can still simulate it, especially nowadays. We have a lot of more computing resources. So you can see that dark matter carves out these filaments, these clusters, they have these voids in here. And if you were paying attention in the beginning, then you might realize that this looks very similar to how galaxies are positioned on the sky. When we make a map of the sky, you have these high concentrations of mass that are clusters. They're connected by filaments, and they have these voids between them. And that is very mirrored in what we see in dark matter simulations. And so this is one of many reasons, among others, that we think that the growth of galaxies and the growth of groups is very much connected to these dark matter filaments and structures overall. And in fact, one of the most common definitions of a galaxy group is a system of galaxies that occupies a common halo of dark matter. So with that, I'm going to thank you all for listening, and maybe McKenna can share your questions.
All right, thank you very much, Zach. I think I saw, yeah, so here is a question from the beginning of your talk. Is the simulation of the early universe or of the current universe as it is today?
Well, let me go back to that slide. I can demonstrate. So this is actually a very sped up simulation of the universe itself. So for reasons I won't get into, Z is sort of backwards from time. So you can think about Z equals 0, meaning today, and then the higher Z is, that's very deep in the cosmic past. So you can see the simulation begins when we're very deep in the cosmic past because Z is very high, and then it's working its way down to 0. So this simulation is showing the evolution of the universe from its infancy stage very early on to what we see today. And you can see that as that progresses, all those smaller units eventually form this cosmic web structure with filaments and voids that you can actually see in the galaxies.
Cool. And you may have mentioned this in the talk, but I will ask for a reminder anyway. How big is this cube, like on a side? How many light years across is that?
I'm not the one who produced the simulation. This is from NASA. So I can't really speak to the size of the cube off the top of my head. But in terms of megaparsecs, it would probably be, close to 100 megaparsecs at least.
Right. These little clumps, those are whole galaxies, right?
Right. So the little clumps are individual galaxies, and then these denser concentrations are like groups and clusters where galaxies are gravitationally being pulled together.
So very, very large scale.
Right. It's extremely large. I mean, if it's a simulation of the universe, so you need it to be extremely large in order to understand. You get a representative sample of all the galaxies.
I don't see any other questions at the moment. While we're waiting to see if anyone has any, what is your favorite part of studying galaxies?
I think that's an interesting question. Galaxies are very cool because in some ways, unlike stars have more predictable patterns of forming. If we look at a star, it's sort of easier to classify. It's easier to possibly tell what its upbringing might have been. Whereas galaxies, almost every single galaxy is completely different in terms of its color, in terms of its shape and physical features. So that complexity, I think, makes the science a lot more interesting.
Very cool. All right. I don't see any other questions. If anyone thinks of any, they can always ask them later, and we'll make sure Zach sees them. Yeah, thank you very much. That was an excellent talk. But so for now, I will hand it on over to Mugdha. Mugdha is another grad student here from UNC. She is a PhD candidate in astrophysics, working with Dr. Sheila Kenepen, and she is working on the Resolve and ESO surveys on looking for black holes in near in galaxies around us. So I will hand it on over to Mugdha.
Hello, everyone. Good evening, and thank you for being here. Is my screen visible? Awesome. And the laser pointer? Perfect. All right. Hi, everyone. Thank you, McKenna, for the introduction, and thank you, McKenna and Zack, for those wonderful talks. I'm Mugdha, and I am a PhD candidate at UNC Physics and Astronomy. I'm also an outreach liaison and diversity officer with the department. And in my free time, I am growing an indoor jungle and also volunteering and training service dogs. So that is me, and I'm so excited to be here to talk to you all about black hole hunting. And to start this off, I actually wanted to give a little background. So my exposure to black holes started in pop culture. There are a lot of songs written about black holes, funnily. As you may see from my background, I am a huge comics fan, and there's a lot of references to black holes and singularities and space-time things in comics, and I was very, very intrigued. There's also this really silly TV show that I thought I should mention. It's called Black Hole High. I used to watch it when I was in high school, and it is very bad science, but it was very entertaining for me at the time, so I was hooked. And of course, Gargantua from Interstellar, this beautiful representation of a black hole that I'm going to keep referencing throughout this talk. So that's where my interest started, and I just wanted to give a little timeline. So in 2014, I watched Interstellar, and I was in awe of Gargantua. It was the most realistic view of a black hole that the public had ever seen until then. And I was just amazed at how different it looked from all the other representations of a black hole I had seen. And I also read about it, that it was the most realistic representation that was ever shown on TV. And I didn't quite understand that at that point. So 2015, I moved to the US and I started my master's in astronomy at the University of Florida, where I was fortunate enough to start researching black holes. And in 2017, I moved to do my PhD at UNC, and I am fortunately still researching black holes. So now I have a lot more appreciation for all the pop culture references. I understand more how Gargantua was realistic and how it and what parts of the movie weren't, and I'm so excited to share that with you all. So to start off the science portion of this talk, I want to quickly recap what is a black hole. So McKenna went over this at the beginning of the talk, so I'm going to be quick and brief. So in very simple words, a black hole is an object whose mass is concentrated in a very, very small volume. So to give a sense of scale, if you wanted to make the Earth a black hole, you would have to squeeze the mass of this big, beautiful world into less than an inch across. I think that would be probably the size of a quarter or smaller, which is crazy. And if you wanted to make a black hole with the sun, it would probably be only 3.5 miles or 5.5 kilometers across. So 5K is a very common marathon running distance. So if you can imagine the mass of all of the sun squeezed into a marathon running distance, that is how small and compact and dense a black hole would be. And now for some bigger scale, a black hole with the mass of 1 million suns would probably be about 4 times the size of the sun. So I just want to draw attention to the size scale here. So in terms of mass, it is 1 million times the mass of the sun. That is a very big number. But in terms of size or diameter, it will probably be only 4 times as big. So again, this just brings me to the point that black holes are very, very compact objects. And what a mass in a small volume or a very dense object means is that it has a very strong gravitational pull that nothing can escape, not even light. So a visualization of that is like something McKenna showed before, is if you can imagine the universe as like this blue rubber sheet, if you place a mass on that rubber sheet, which is synonymous to the space-time as you have heard it, that rubber sheet is going to have a distortion. It's going to curve, it's going to be distorted by the mass. But because a black hole is so massive, but so small, that distortion is extreme. It's not going to be like a gentle curvature, it's going to be an extreme well. So this is literally called a gravitational well. And this extreme distortion is the reason that nothing can escape the black hole. So this event horizon marked with this ring over here, that is the point of no return, where if anything crosses that, not even light can turn around and come back. So that was my brief explanation of what is a black hole. So going back to this picture of Gargantua and Interstellar, this represents one type of black hole. It's a supermassive black hole. And these supermassive black holes can have anywhere between the mass of 1 million to 1 billion suns. That is massive, even by space standards. So how can we find these black holes? So there are, I will preface this whole talk by saying that there are so many different methods of how we infer the presence of black holes, and I will not get into every one of them because there would just be no time for all of that. But I'm going to talk about some really interesting ones, and I will first start with accretion disks. So this picture where you see this nice glowing ring-like structure, that is what an accretion disk is. So here is a NASA simulation of what a black hole looks like, very, very similar to that picture we saw from Interstellar. And what this is it's a disk of glowing hot dust and gas, which is circling the black hole. But I just told you a couple minutes ago that the gravity of a black hole is so strong that nothing can escape it. So then how is there all this stuff around it? That sounds absurd, right? But it isn't. So if you think about, say, a bathtub or a sink filled with water, and if you were to pull the drain plug, all the water doesn't immediately get sucked down the drain, even though that's eventually where it's going to go, right? So water slowly starts circling around the drain and will trickle down the drain until there's no more water left. And that's exactly what happens with black holes. So the material around the black hole, which is dust and gas, a cosmic dust and gas, kind of settles into this disk that starts circling the black hole. But because of the intense gravity of the black hole, this gas and dust is circling really, really fast. So they start becoming very hot and they glow like how a hot piece of coal would start glowing red. That's exactly what happens, and that's why you see the accretion disk. So then, okay, if that's something that you can buy, there's an accretion disk around this black hole, then you may be wondering, why this weird structure? Like, why does it look like there are two rings? They're actually not two rings. It is just one ring, but what you're seeing here is the image of the far side of the disk. So what that means is that the gravitational force around the black hole is so strong that it literally bends light. So it can bend light the same way a lens of your spectacles or magnifying glass does. So what you're seeing is the disk that is behind the black hole. You're seeing its image up on top. And in the same way, you're seeing what's on the underside of that disk behind the black hole on the bottom. So it is still just one disk around the black hole. You're just able to see what's behind it, which is pretty cool if you think about it. So the first picture of a black hole McKenna already showed us was in M87. And just for a sense of scale, this is the galaxy. This is the central zoom part of the galaxy. And that tiny speck over there is what this picture of the black hole represents. It is a very, very small part of that galaxy in the Virgo cluster. And I think this particular image was compared to taking, to be able to clearly see a moon placed on the surface, to be able to clearly see an orange placed on the surface of a moon. That is how difficult, or that is what the scale of this image is, if you can think about it. And so it is, and this picture was taken in 2019. So we have known for a very long time the existence of black holes, and we have had so many other ways of inferring that, but we never had a picture of it until 2 years ago. So it is amazing how technology has improved and all the things that we can see. So going back to that simulation, you may think, how can these images be the same? They look nothing alike. I mean, there's some glowing stuff, but this looks like a ring, this looks like a donut. What's going on? So something is different about these two. And what is different is the way we are viewing it. So the way the black hole appears to us depends on its orientation. So this picture, which is kind of like the simulation that we saw on what we see in Interstellar, is that you are viewing the black hole edge on. So it's kind of like when we look at Saturn in the sky, we see the planet with its rings cutting across. That's exactly the kind of angle that you are looking at this black hole. But if you had a spaceship and if you were to travel and look at Saturn from above, what you would see is the planet, but you would just see a circle, a ring around it. So the same way for the black hole, there is nothing inside because you can't see the black hole, but all you see is the ring of light around it. So those two pictures are the same. It's just different based on the angle that you view it from. So moving on to the next way of hunting these supermassive black holes are using the orbits of stars. And this method is a little special because this method was very recently used in our own galaxy. So this, if you look at the night sky and if you know where to find Sagittarius, the constellation, it is supposed to be of a hunter, but it honestly looks like a teapot, and that's what most people identify it by. So if you look at the teapot, and the spout of the teapot is directly pointing to the galactic center. And the galactic center is where we had long suspected this Sagittarius A star to be a supermassive black hole. But very recently, we actually got confirmation of that. So what scientists used were actually mapping out like the wonky orbits of stars in near the center of the Milky Way. So in this animation, all these bluish purple things are individual stars, and this star symbol actually is at a focus of these ellipses that the stars are making. So this animation is going to play back again. I want you to follow this yellow ellipse. So this one right here. So this particular star starts to go slowly, and then the moment it reaches closer to that star-shaped symbol, it accelerates really fast and then swings back and then slows down again. So those kind of orbits were initially the suggestion that there's something really massive at that focus of all those ellipses. So by mapping all these different stellar orbits, astronomers then confirmed that you have something the mass of 4 million suns placed somewhere in the size of in an area the size of our solar system, and they concluded by eliminating all the other options that it was indeed a supermassive black hole. And Dr. Andrea Ghez and Reinhard Genzel were actually awarded the 2020 Physics Nobel Prize for this work, which was very, very exciting. So to recap, supermassive black holes, they have the mass of about 1 million to 1 billion suns, and they are found in giant galaxies. So that's an actual technical astronomical term that we use, giant galaxies, kind of like the Milky Way and M87 that we saw, and Andromeda and other giant galaxies. And we have very strong reasons to believe that almost all giant galaxies have these supermassive black holes in the center. We're not entirely sure if all of them are actually have this accretion disk or ring of light, or all of them are actually actively eating up material, but we have very strong evidence to believe that they are present. So now there is this question, where do these supermassive black holes come from? So there is one theory that they could come from stellar mass black holes that go through some very, very complex process and then eventually become supermassive black holes. And stellar mass black holes are actually the remnants of a dead star. So when a really, really massive star dies, all its matter just cannot help but collapse upon itself to a point that it becomes so small and so dense that it becomes a black hole. So for some comparison between stellar mass and supermassive black holes, stellar mass black holes would have the mass from anywhere between 3 to 100 suns, versus supermassive black holes with the mass between 1 million to 1 billion suns. And stellar mass black holes technically could be found anywhere in a galaxy. The only requirement is that there should have been a massive star to die in the first place. But that could technically happen anywhere. So how are these stellar mass black holes found then? So one such way that literally made waves across the universe was gravitational waves. So this picture over here is showing, these blue and red lines are showing the actual signal that LIGO, which is a collaboration of astronomers and physicists worldwide. So they have two laboratories in the United States, in Washington and Louisiana, where they saw these signals. And this signal was the first ever confirmed detection of a gravitational wave in human history. So what they concluded after thorough and careful analysis was that this gravitational wave came from the merger of two black holes, one that was about 25 times the mass of the sun, and one that was about 31 times the mass of the sun. So these two black holes, this is an artist's impression. So these two black holes merged, and then you had a final black hole that was about 53 times the mass of the sun. So if you look carefully, 25 plus 31 gives you 56. And we may have heard over several years that matter can neither be created nor destroyed. So where did that three times the mass of the sun go? That was actually converted into gravitational energy, which is what was actually detected by these laboratories. So that was the first time that we ever saw it. And I have a little movie showing how the gravitational waves are actually produced. So in this movie, the coloring is based on the strength of the gravitational force. So the dark blue is like normal, and the green and going to red is just getting stronger and stronger. You're getting stronger and stronger gravitational force. And these are two black holes that are spiraling each other. And you can see there are two the gravitational wells that are very, very deep and very evident. And now as they are coming closer together, they are spiraling faster and faster. And now they're almost merging. And the simulation is kind of showing you how that merger is happening and what is happening to their gravitational potentials. And now they have merged. The movie is frozen. And you see that their gravitational potential has become one, and you just have one massive black hole at the end of it. And now this sends ripples across space-time. So these purple and pink circles you see are literally ripples that are sent out from space-time. So as McKenna said before, it would literally be like if you threw a pebble into water and you see that rippling effect. And that rippling effect was sent all the way to Earth. It's just, that's not ripples in water, it's literally ripples in space because of gravity. And if you look down here, they show you the signal of like when the black holes are spiraling and they start spiraling faster, and then and once they merge, you have this big chirp, and then you have nothing. So that is exactly the kind of signal that LIGO observed, and that's how they detected the first gravitational wave. And again, a sense of scale, this, even though it looks so obvious in the simulation, this happened very far away from Earth. So the scale of disturbance they were looking for was literally the size of an atom in a laboratory that was about 4 kilometers long. So a very, very tiny disturbance. And again, it amazes me how technology has come so far. So going back to this picture of supermassive black holes coming from stellar mass black holes, if you look carefully, there seems to be a little disconnect, right? Like 100 suns, the mass of 100 suns is very different from 1,000,000 suns. So it's like, is there something missing in between? And we definitely think that there is something missing. And that missing link is intermediate mass black holes. So intermediate mass black holes, again, for comparison, could have a mass anywhere between 100 and 100,000 suns. And we think that they should be in the center of smaller galaxies called dwarf galaxies, so not big ones like the Milky Way, but smaller galaxies that are in an earlier evolutionary stage than where giant galaxies like the Milky Way are. So hunting for these intermediate mass black holes is a relatively new frontier in black hole astronomy. So this is a picture of dwarf galaxies, real dwarf galaxies that actually host these intermediate mass black holes, and these dwarfs look very different from the regular picture of big beautiful galaxies like Andromeda and the Sombrero Galaxy that we're used to seeing. They're very small, but in the universe that's really close to us, these are actually the most common galaxies. So by only looking for supermassive black holes, we're probably missing a lot of the black hole population altogether. So these intermediate mass black holes were actually found by tracing black hole signatures in radio waves in a method that was very similar to what you would do to find supermassive black holes. And that brings me to this point. So we have found some intermediate mass black holes, but not as many as we expect. And one reason might be that they're smaller and harder to find. So, we're just finding fewer. But another reason is that we're also relying on methods that have been used to find supermassive black holes. So we just saw the difference between finding supermassive black hole and stellar mass black holes. So it is not crazy to think that we need to modify these existing methods or find new methods to find these intermediate mass black holes. And that is exactly what my thesis topic is focusing on. We are trying different methods to find these intermediate mass black holes in these dwarfs, just because we have so many of them close by to us, and they just make really good laboratories for what maybe was happening when the universe was overall very young, like in the past. So just an updated timeline to wrap up, that now in 2021, my thesis topic is finding intermediate mass black holes in these dwarf galaxies. And that is kind of where my black hole journey is at in the present. So I will end with this, and thank you for listening to me. And do we have any questions?
Thank you very much. That was great. There are a couple of questions so far. So the first question, these particular singularities, black holes, are they the remnants of the earliest stars in the universe?
Are we talking about like black holes in general, or?
This was a question that was asked at the very beginning of your talk.
Okay. So I'm just getting black holes in general. Okay. So yes and no. So okay. The honest truth is that we don't exactly know how black holes form. That is a very, very active area of research. We have two hypotheses. We have one hypothesis is that lots of massive stars collapsed on themselves and then merged and then came together and then formed bigger black holes, and then those merged in bigger black holes, and those merged and then have bigger black holes. It just feels like that's why I said that this kind of feels like a stretch, because you're going from 100 solar masses, or the mass of 100 suns, to mass of 1 million suns. So there are also other theories that at the very beginning of the universe, when matter was all kind of close by and condensed, if you will, that there could be these pockets of mass that basically got attracted to each other super fast and got super close and then just collapsed on them all by themselves to form these supermassive black holes. So we're not sure we probably think that both things happened. We just don't know which ones are more common. I hope that answered the question.
Yeah. Okay, so the next question is, do the kinds of stars that collapse into or fall into black holes affect the properties of the black holes?
Sorry, could you repeat that?
Do the kind of stars that collapse into or fall into black holes affect the properties of the black hole?
Yeah, so again, if a star collapsed in on itself and formed a black hole, it would probably be around a stellar mass. And I say this, that would start at the mass of 3 suns, just because that is the maximum limit of what a neutron star could have, which is the next least massive thing that you can have compared to a stellar mass black hole. So if it was a star collapsing to form a black hole, it would be very different. But if it is a star that is eaten up by a black hole, I'm not sure if that actually affects the properties of the black hole, except for the fact that if there's a more massive star falling into the black hole, then the black hole will grow that much faster. Just because once something goes into the black hole, that information is lost forever. So I don't, as far as I know, I don't think what goes into the black hole matters. I think it's just how much and how fast. If that makes any sense?
Yeah. Okay, next question. Do you ever find singularities without a galaxy or without stars around them?
Oh, wow. Okay. Okay, so I'm not a singularity mathematical expert, so I may not be 100% right on this, but a singularity, as far as we know, is a mathematical construct for what is inside the event horizon, because we just don't know, because as far as we know, all our laws of physics break. So we don't really know. I think it's just a convenient way to make the math work by what we call a singularity. But if you're talking about, does a black hole exist without a galaxy or without stars around it, maybe it could. And if it did exist in space between galaxies where there's, some gas or something, but nothing else, we wouldn't really be able to see it. So the answer is it could, but I am not sure of like what condition you would need to make that happen, because I feel like if you had to have a black hole in a particular place, that means that there was a lot of mass that somehow got condensed. And once you have a lot of mass in one place, you're going to attract a lot more mass. So I feel like just by having the condition to build a black hole, you're automatically going to build something like a star cluster or a galaxy around it.
Yeah, that makes sense. I'm not seeing any other questions at the moment, but I have one.
Sure.
So in the video you showed showing the orbits of stars around the center of the Milky Way, it looks like they're moving sort of in all sorts of like three-dimensional orbits around, like they're not really in a ring. So why then does the material that falls onto the black hole orbited in a ring and not sort of a cloud around the black hole?
I think the scale that these stars are showed on is very, very different, right? Because we said that what these stars are orbiting is something within an area of our solar system, right? Very, very. So this is already way, way outside the solar system. So this is just in the center where there's already a lot of stuff. So you do have random orbits, and the center of our galaxy has like a little bit of a bulge. So I think I would expect you to have more random orbits. And why the accretion disk is a disk is interesting. So that is like literally at the very small scale. That's like literally just immediately outside the event horizon. So I think like everything in physics, it is easier for something spinning really fast to become a disk rather than a ball, which is why the solar system is flat, the rings of Saturn are flat, and just by analogy, a lot of other things, just spiral galaxies are flat. So anything moving really, really fast will automatically want to settle down into a flat morphology.
So just because those things are moving faster, they settle
really
faster into a disk. That makes sense. All right. We'll give everyone a few more seconds to see if there are any last questions, but I'll give you the same question I gave Zach. You talked a lot about why you got interested in black holes during your talk, but what is your favorite thing about studying black holes?
Well, if it is already not evident, they are very, very cool and weird objects. So everything about it, I think it's just very interesting to know that that like whenever we thought about black holes, whenever I thought about black holes before I was actually studying this, I just always thought about these like huge, massive monsters that are just going around and eating everything. And slowly I'm like realizing that that's not true. It's very hard to get something to actually go inside a black hole. And like I just said, they're not very big for the amount of mass that they have. So I think it's just very cool that something that is literally in such a small, that occupies so little space has such like massive repercussions. Because they not only affect their immediate surroundings, but they also affect how galaxies grow and evolve. And there's something that, they're just so cool.
Yeah. Well, thank you both, Zack and Mugdha. Those were excellent presentations. Very, very interesting. Yeah, not seen any last questions. So yeah, round of applause virtually. I don't know, for our speakers. And Astronomy on Top Triangle will be back next month on April 6th. So we will see everyone then.
Thank you so much for having us. This was so great.
All right. Okay, stream.